Hello there and welcome to another session of solving PYQs on the subject of DECO. The questions are related to all the modules and this will be part 2 of solving the PYQ questions. So the first question is that a computer uses a memory unit with 256k words, 32 bits each. The binary instruction code is stored in one word of memory. The instruction has 4 parts. So the instruction has been stored in one word of memory, okay? And it has 4 parts. It has been divided into 4 parts: the indirect bit, OP code, a register code that specifies one of the 64 registers. So that means the system has 64 registers, and the register code is used for specifying either one of them. And finally, we have the address part. The first part says how many bits are there in the OP code, the register code part, and the address part. Since we can see from the initial statement that we have 256k, over here k is 1024 bytes. So we have 256k, which can be split into 2 power 8, which stands for 256, and 2 power 10 can be used for k. Hence we get the summation of the powers as 2 power 18. This will give us 18 address bits. So based on the amount of words we have, the amount of data, we can get the address bits. So for the address bits, we have 18 bits, which is the power of the 2. This we get on the simplification of the number of words. Second, we need to find out the register code. Since it mentions that there are 64 registers, then we can easily find out the 2 power n lines for the register, okay, or the bits. So 2 power 6 will give us 64. That means 6 bits will be used in order to determine one of the 64 registers. Since it mentions over here, you need to choose one of the 64 registers. Hence we have 6 bits for the register code. Finally, we have one indirect bit, as always, in an instruction format. So the summation of these three values, 18 plus 6 plus 1, gives us 25. The size is already given. We have 32 bits of the words. Okay, so the instruction code is basically called a word, and it is 32 bits. So since we have 32 bits and we already found the 3 parts, for the fourth part, which is the OP code, we can just subtract the 2 and we'll get 7. So there are 7 bits for the OP code. Part B asks us to draw the word format, which is simply just putting our values that we found in part A into the instruction code format. So the first part will be the mode, the addressing mode, then we have the OP code, register, and finally we have the address. You will write the size of the bits above the above the addresses and all to mention what the size is. And finally you will have 32 bits in total. Part C says how many bits are there in data and address inputs of the memory. So the data, as we can see from here, the data total is 32 bits, and finally the address is 18 bits. So this question is basically connected to the first part. As long as you can complete the first part, part B and C are pretty easy. This question is based on the bus system that we studied for the computer organization for a basic computer. It says that the following control inputs are active in the bus system shown in the given figure. For each case, specify the register transfer that will be executed during the next clock transition. So as explained in the lecture for the bus system as well, we can see that we have selection lines 111. This means that the memory address will be loaded onto the bus. It will copy onto the bus, and in order to make sure that the memory address is copied, you also have to look at the memory part, which says it's set on read. That means the memory will be read and the data from the memory will be copied onto the bus. Finally, we have the load part of IR set to 1. So the load register of IR is set to 1, which is here, load of IR. Hence, the memory that has the data from the memory that was copied onto the bus will be loaded onto the IR register. So part A says memory is read from memory read to the bus and then loaded onto IR. Similarly, the second part talks about 110. The 110 sequence helps us in selecting the temporary register over here, TR, which is the sixth one. So 116 refers to 6, and hence TR is selected to be loaded onto the bus. Then we have the load register of the program counter set to 1. Hence we will load the temporary register onto the bus, and then the data will be loaded into the program counter PC. Fine. In part C we have 100. 100 refers to the accumulator. 100 refers to the DR, sorry, not the accumulator, DR. 100 is for DR, as you can see over here, third one. So 100 stands for, so since DR is loaded, the load value of DR is set to 1. We have DR over here, load set to 1, and we have 100, which is the selection for the accumulator, fourth one, 100 stands for 4, so accumulator is loaded onto the bus. Okay, copied onto the bus. DR has the load open, and we can also see that the memory is set to write. So the memory function is set to write. Hence, the data that has been loaded from the accumulator onto the bus will be copied into the DR as well as the memory. So from AC it will go to bus, and then it will write to the memory as well as the DR. In the last part, we can see that it is set to 000. Hence, none of the registers or the memory are going to be loading to the bus. The bus will be switched off for all of them. We have AC from load. Okay, we have the load of AC turned on. That means whatever data is there, it will be loaded onto AC. AC is connected to the adder logic, and over here we say the adder has the add operation. Hence, the adder will add any data and it will send to the AC. It will load it onto the AC. But as you can see, the adder has 3 different inputs. It's either the AC itself, or it is from DR, or it comes from the INPR. So we'll say that the input for the adder logic circuit comes either from the DR or INPR and is loaded to AC. Hence the function, the statement that's been executed, AC plus DR, and stored to AC. The next question states as follows, that the following transfers are to be executed, which are given in a system, and we have these 4 different parts that we need to complete. So the first part is that we need to find the binary value for the bus selection inputs of S0, S1 and S2. We also need to find out which resistor will have the load input set to 1, okay, which will be active. The third is the memory read or write operation, whether the memory will be read or will it be written. And finally, on the fourth one, we have the operation of the adder and logic circuit if it needs to be performed. So in the previous bus question, we had seen that there was a table given to us, and we had explained what systems are going to happen onto the bus accordingly. Over here we are supposed to make the same table. We are given 4 different statements that are to be executed. The first statement is PC will be added to AR. In order to add PC to AR, PC must copy to bus. So we will use the code for the PC. Okay, PC is connected to the bus using the sequence of 0, 1, 0. Hence S0, 1 and 2 will be set to 0, 1, 0. Load of AR will be set to 1. It will be active so that AR can have the data copied into it. And since it does not have anything to do with the memory or adder, they will be set to null. In the second part, we are reading from the memory the address, okay, and we are adding it to IR. Hence, memory will be set to read, okay. And since memory is connected to the bus using 111, so the select lines will be set as follows, so that the memory can be copied onto the bus. Finally, since we are loading it onto the IR register, it will be the load of IR will be set to 1 or active. In C part, again we are copying data from TR into the memory. So in this point, we will be connecting the temporary register to the bus, and temporary is connected using the select outputs of 110. Since we are not loading it into any register, so there is no load option, but we are writing it onto the memory. Hence the write function for the memory will be set to active, and then data from TR will be written into the memory. Finally, in D part, we have 2 different tasks being performed together, that is DR transfer to AC and AC transfer to DR. So in order to complete these, first we will consider AC, which is connected to the common bus. So in order for data to go from AC to DR, we will have to allow AC to copy its data onto the bus, which happens using the inputs of 100. Then we will be loading both the registers AC and DR. Since they're both registers, they have a load function in them. They both have to be set to active so that data can be transferred into them. And the adder that is connected to the AC and has DR as an input, the function that the adder will perform is it will transfer data from DR to AC. Hence both the operations will be performed, where AC will copy data from the bus to DR and DR will send data through the adder to AC. The next question is it states that there are 2 instructions needed in the basic computer. What are the 2 instructions needed in the basic computer? To set the flip-flop E to 1. So in order to set E to 1, the first condition will be to clear whatever is in E. So we will make it 0. So the function is CLE, clear E, and then we'll complement the value, which is 0 will be complemented to 1. Hence E will be set to 1, and the complement is done by CME. So complement E. The next question says explain why each of the following microprograms cannot be executed during a single clock pulse in the system shown. So specify the sequence of memory operations that will perform the operation as follows. Okay, so part A is, it states that the memory at the memory address of PC, data is stored, copied from there and stored to the IR. The reason why this won't happen is the program counter PC does not go directly to memory. PC is connected to the address register AR. So first PC has to transfer the data to AR, and then from AR it will be transferred to IR, and hence it cannot be transferred directly from PC to AR to IR. It has to go through the intermediate AR. So the steps, the sequence that will be used for the first operation is PC will be transferred to AR, and then from the memory address of AR it will go to the instruction register. Part B says we add TR to AC and then we store it in AC. The issue with this one is that TR is not connected to AC directly. Okay, so add operation must be done with the DR. So in order to perform any operation on the accumulator register, it has to be either the input register or it will be the data register. Since the input register is not connected to the bus, we will be using the data register. So we'll transfer the data of TR into the data register, and then we can perform the adding operation by doing AC plus TR and storing it into AC. The third operation is DR plus AC stored to DR. In this case, it says that AC does not change. So when we do DR plus AC to DR, the result of addition is transferred to AC, not DR. Okay. To save value of AC, its content must be stored temporarily in DR or in TR. So what we are going to do is, first we are going to do DR will go to AC and AC will go to DR, and then we are going to add both of them and store them to AC, and finally we are going to flip them again. This is because whenever we do addition in AC, so the accumulator logic takes in the input from DR and it adds them. From AC and DR are added, and then it's stored to AC instead of storing to DR. So the system is reversed. So in order to do the opposite, we are going to have to store the AC value into DR, the DR value into AC, then we'll perform the accumulator logic, and finally the DR will be stored back to AC and AC will be stored back to DR, which will hence be the actual procedure of performing this statement. In this question, we are to consider the instruction formats of the basic computers shown, and then we list the instructions given for each of the following 16-bit instruction. Okay, so we have a 16-bit instruction and we have to list the instruction or find out what the instruction is, and also give the 4-bit hexadecimal code along with explaining in your own words what the instruction is going to perform. So whenever we are given a 16-bit instruction code, we know there are 4 parts, so this is going to be into 4-digit hexadecimal, 4-bit hexadecimal. The first part is going to be used, and from the first part we are going to identify which sort of instruction this is. Since it is from the range of 000 till 110, this is a memory reference instruction and I is 0 here, hence addressing mode is direct. Through this we can tell that I is 0 and it is 001, so it is the first instruction of the memory address instructions, that is add. So we will perform add onto the following data. This is the instruction or the address for the data. So 0 will be 0 in hexadecimal, 0010 is 2, and 0100 according to the question 0100 is 4. So 024 with base of 16, which means it's the hexadecimal number, will be added. Hence when we write it in complete hexadecimal, convert the whole thing to hexadecimal, it will become 1024 hexadecimal base. The statement is that we add the content of M at memory 024 to the AC. So add 024 to AC. In the second one, we are going to decode this instruction. It is again a memory instruction. We can see that the addressing mode is indirect, and then we have 011, and we will be using the table for the memory reference register. Over there we can find out that the function at 011 is to be performed, that is STA. So we will store A, okay, store in AC the value at the indirect address. So the indirect address will be, as we decode this binary to hexadecimal, it will become 1, 2 and 4. So 124 will be the address at which the effective address is stored. Hence the value hexadecimal of this is B. So B124 in hexadecimal, this will be the conversion, which is the part it's asked to convert to hexadecimal. and then we will perform the operation of storing in the memory address. The memory address location will be having another memory address, that is 124. So it will point to the to 124 and then it will store over there. Finally, in part C, again we can do the same thing. It is 111 over here, so we find out that it is a register reference instruction, and it is 0 also. So 0111 refers for register reference. Convert the whole all 16 bits to hexadecimal, that will give you 7020. Both are zeros over here, and this is 2. And the function at 0111 is increment AC, so we'll be incrementing the accumulator. In this question, we'll be seeing that a digital computer has a memory of a unit with the capacity of 16,384 words, 40 bits per word. So there are 40 bits per word, and this is the number of words. The instruction code format has 6 bits for the operation part, okay, 14 bits for the address part, and there is no indirect bit, okay. So there are 4 parts in which these 6 bits are for operation part and 14 bits are for address part. 2 instructions are packed in 1 memory word, so the 2 instructions are put into 1 memory word, hence the 1 word has a double instruction in it. And a 40-bit instruction register IR is available in the control unit. So the instruction that is in 4 different parts and has 2 instructions in it is stored in IR. So we are supposed to formulate a procedure for fetching and executing the instruction for this computer system. So first of all, we can draw a rough diagram to understand what sort of instruction we have. We have the operation code 1 and address 1 for the first instruction, and then we have OP code 2 and address 2 for the second instruction, each of them being 6 bits and 14 bit, giving a total of 40 bits. And the OP code is sent to the decoder, as we remember from the diagram we studied earlier in the lecture, that the OP code is the code for selecting either one of the multiple different operations that the system has. So both of the OP codes will be connected to different decoders, and our procedure for fetching and executing instruction will be as follows. First, the system will read the 40-bit double instruction from memory, and it will store to IR, and then the program counter will be incremented. You have to increment the program counter so that it points to the next instruction. The second step will be to decode the first OP code. Since we remember, the instruction cycle is always about fetching, decoding and executing. So the second step will be to decode OP1 and execute the instruction using the address 1. So once we decode this, we know what operation is supposed to be performed. Then we find the operand from address 1 and execute it accordingly. Then we will decode the second operation code. We'll find out what the operation is, and then using the operand at address 2, we will be executing the second instruction. Finally, we will go back to step 1 and repeat again and again until the halt condition is encountered. The system shown in the figure, whatever figure must have been given, uses a control memory of 1024 words of 32 bits each. The micro instruction has 3 fields, and the micro operation has 16 bits. So the instruction has 3 fields. There are 3 parts of the instruction, and it has 16 bits in the micro operation. First off is how many bits are there in the branch address field and select field. So the branch and select field, we need to find out the number of bits in them. Since we have the micro operation part set to 16 already, the question tells us from 1024 we can find out the address bits, as we saw in the previous questions. 1024 can be denoted by 2 power 10, which means 10 address bits are there. Hence we have 10 address bits and 16 micro operations. We already have 2 parts and the third part is missing, and we are already given with 16 bits of the instruction, so we'll add these two and subtract from 32, which will give us 6 bits remaining for the select line. The B part tells us if there are 16 status bits in the system, how many bits of the branch logic are used to select the status bit. So for 16 bits, how many select lines? Basically this is a basic calculation of 2 power n equals to 16, so we need 4 different bits for a selection of 16 bits. So 4-bit code will be used for selection of 16 bits. Finally, how many bits are left to select an input for the multiplexers? We can see that the instruction code has 6 select lines over here total, and since 4 are used for the status bit system, the remaining are 2 bits, hence the last 2 bits will be used for selecting an input for the multiplexers. The control memory in figure has 4096 words of 24 bits each, How many bits are there in the control address register? Again, 4096 will be denoted using 2 power 12, and hence we have 12 bits in the address register. How many bits will there be in each of the 4 inputs shown going into the multiplexer? So the multiplexer also has 12 bits going into each of their inputs. Finally, we have what are the number of inputs in each multiplexer and how many multiplexers are needed. So for the number of multiplexers, we can see that the number of registers will help us in finding out the number of multiplexers. So since we have 12 bits in each register, we will be having 12 multiplexers for each bit, and the size of the multiplexer is 4:1, since it already says the 4 inputs are shown going to the multiplexer according to the diagram, hence the size will be 4:1. In the following, we are supposed to use the mapping procedure to describe the first micro instruction address for the following OP codes. The first one is 0010, 1011 and 1111. So for mapping the instruction, there is a basic format. You add a 0 to the left of the code, and you add 2 zeros to the right. This is basically done to increase the size of the format from the OP code from 16 bits to 128 bits, because it becomes from 4 bits it becomes to a 7-bit selection, and all you're going to do is you're going to just add 1 0 to the right, to the left, and 2 to the right. That way it increases the mapping. This is the mapping procedure. A bus organized CPU similar to the figure that is given has 16 registers, 32 bits each, and an ALU along with a destination decoder. The first question is how many multiplexers are there in the bus A, and what is the size A for each multiplexer. So the confusion here is since we studied the ALU, we remember that there is only one mux. There are two mux, one for A bus and one for B bus. This is not going to be the case over here. We are discussing about the bus over here. Okay, so how many multiplexers are there in the A bus? The way we studied the ALU system of a CPU, it was a simple one where we did not show the bus in detail. So if the CPU has 32 bits each, then there will be 32 multiplexers. Here, as you can see, 32 multiplexers, and for 16 registers, so the size will be 16 into 1 each. Okay, since multiplexers are on the basis of the number of bits, and the size of the multiplexer depends upon the number of registers. So 16 is to 1 multiplexers, 32 for each bit. And then the next one is how many selection inputs are needed for mux A and mux B. We have the size is 16, hence for 16 size we have 4 selection inputs from the formula of 2 power n. And now the part C is how many inputs and outputs are there in the decoder. The decoder will have the inputs and outputs on the basis of the number of registers. Since we have 16 registers, so we will have a 4:16 line for the decoder. So 4 selections will give you 16 different combinations for selecting any one register from the 16 registers. Part D says how many inputs and outputs are there in the ALU for data, including input and output carries. So over here, the input and outputs, this refers to the number of bits for the ALU. Since we have 32 bits each, so the input data will be A plus B. A is 32 bits, B is 32 bits plus a carry bit. So 32 plus 32 plus 1 will give you 65 input. The output is only 1, so we will have an output whatever function is performed on A and B, we will get a single output which will be 32 bits plus a carry bit if there is, so we will have total number of 33 output lines. Part E says formulate a control word for the system assuming that the ALU has 35 operations. So select A, B and D will have 4 select lines each, as we discussed earlier in the part. The ALU will have 6 select lines. We will not have 5 over here because 5 would give us a number smaller than 35, and since we have 35 operations that we need to perform with the ALU, we'll be using 6. Although 6 will give us a larger number, a much larger number than 35, it will be 64. We can still arrange only 35 operations on specific selected combinations of the OPR. Thus the total size will be 18 bits for our control word. Again, this computer is about a memory unit where it has 256k words. Since it has 256k words of 32 bits each, we can find out that 2 power 18 will be our address lines, 18 address bits. Okay, and the computer has the instruction format with 4 fields. So it is mentioned that there are 4 fields in which there is an operation code, a mode field. Okay, so there is a mode operation code, to specify the mode is specifying one of 7 addressing modes. Okay, so the register reference field is also specifying one of 60 processors, and then we have the memory address. So we already found the number of bits in the address, 18. The register is specifying 60 of them, so we'll have 2 power 6, that will give us 64. Hence we can have 6 selection bits, and then we have a mode, one of 7 addressing modes. Hence we will use 2 power 3, that will give us 8, which is greater than 7. Hence we can we can handle 7 different addressing modes in 3 bits. Okay, so finally we have 32 bits each. So to find out the opcode size, we will have to do 32 minus the 3 bits that the 3 different modes that we found. We'll get opcode as 5. Now we have the instruction that is stored at 300. So we have an instruction stored at the location 300, and its address field is stored at 301. The address field has the value 400 stored into it. A processor register R1 contains the number 200, so this is the processor value. Evaluate the effective address in the following modes. So the direct address will be 400. Okay, so the direct address towards the data that we have is 400. The immediate address is 301, which the immediate address points towards the effective address. The relative address will be 302 plus 400. The relative address is done where we add the direct address with the program counter. Program counter is always considered for the next instruction, so 400 plus 302 will be 702. The register indirect will be 200. It is given already in the register processor. Okay, and the indexed will be 400 plus 200, that is from the register processor. Register instruction, that will be 400 plus 200, will give us 600. In the following 8-bit computer, it has a register to determine the values of C, S, Z and V after each of the following instructions. The initial value of the register R is in each case is hexadecimal 72. This is the initial value, and the numbers below are also in hexadecimal. So we are going to add the operand C6 to R. So 72 plus C6 is going to be done. After the operation is done, we are going to find the final value, and we are going to make the following conclusions based on the values we studied. So C is the carry bit, so if we have a carry over here, which we do, C will be set to 1. S is the sign bit, there is no change to the sign, hence there is no change to S. Z is 0, when all are 0, Z is supposed to be 1. Since there are 1 bits over here, so Z is 0, and we do not have any overflow, hence it is set to 0. Similarly, we can solve it for all of these questions. You have to perform the operation, and accordingly you can change the values of C, S, Z and V, which are the status bits. The program in a computer compares two signed numbers A and B by performing the subtraction A minus B and updating the status bits. Let A be this number and B is this number. First you will evaluate the difference and interpret the binary result. So we will be subtracting A and B. We will find their 2's complement and then we can subtract accordingly. Once we get the subtraction, we get the 9 bits from the subtraction. And then in B we have to determine the value of the status bit S, Z and V. S equals to 1 because of the sign reversal. This will happen because a smaller number a bigger number is being subtracted from a smaller number, hence there is a sign reversal. And then Z is 0 because we have ones in an output, and V is overflow. Overflow lets us know about the differences in the bits due to the overflow. You can understand more about these conditions in the PPT where we've studied about it. Then we have the listing of the conditional branching instructions from table that will have true condition. So we had a table about the status bits where we found out that there are true conditions. In this case we have 3 true conditions where branching will happen when A is greater than B. Okay, and then in this condition A is greater than B because A is plus positive 65 and B is minus 124, so A is greater than B. Then branch if greater than or equal to, because A is greater than, so the greater than or equal to equation statement will also be satisfied. And finally we have the branching when A and B are not equal. So when branch and not equal, so A is not equal to B, hence these 3 conditions will be satisfied. In this we are supposed to perform the arithmetic operation of A plus B multiplied by C plus D with a stream of numbers. The pipeline has to be configured, so we have to draw the pipeline. In order to draw the pipeline, we are going to take R1 and R2 registers and you're going to input A and B. They'll be sent to the adder, and then it will come out into R5. Same way R3, R4 will have C and D, they'll be added to the adder and it comes to R6. R6 and R5 are sent to the multiplier, and finally we get the result in R7. This is how we can draw the pipeline for I numbers through from I is 1 to 6. I can be 1 to 6, so you don't need to worry about that since we only have to draw the pipeline over here. Hence we will show the pipeline format. In this we have to draw the space-time diagram for a 6-segment pipeline showing that the time it takes to process 8 different tasks. Okay, since the pipeline is 6-segment, we will have 6 segments over here. It is performing 8 different tasks. So at the first time it will be T1. Okay, at time 1 it will be at segment 1 T1 will be performed. Then at 2 T1 will reach its T2 stage, and T1 of the second task will be fetched. Accordingly we can perform the instructions. Since we are doing 8 tasks, so T1 all the way to T8 will be written, and then the second segment will start at the second part from T1 till T8 again, and you go all the way till T8 for the 13th part. This will show us the space-time diagram, and then we can find out the number of cycles using the formula of k plus n minus 1 tp, where we have k as 6 segments as we have mentioned in the question, plus n minus 1 8 minus 1 tasks, okay, equals to 13 cycles, and tp will be the time that will be given for performing one single task. Since it is not given, we only have number of cycles and not the time. So k plus n minus 1 gives us 13 cycles. It takes 13 cycles to perform all the 8 tasks in 6 segments. Next we are to determine the number of clock cycles that it takes to process 200 tasks in a 6-segment pipeline. So we have 6 segments, n is 200, so the clock cycles that it's going to take is k plus n minus 1. So 6 plus 200 minus 1 will give you 205 cycles to perform these many tasks. The next question is, a non-pipeline system takes 30 nanoseconds to process a task. Same task can be processed in a 6-segment pipeline with a clock cycle of 10 nanoseconds. Determine the speed up ratio. So S speed up ratio was given by NTN upon k plus n minus 1 TP. We studied this in the equation in module 5. And speed up ratio for 100 tasks. What is the maximum speed up that can be achieved? Since Tn is given as 15 nanoseconds and k is given to us as 6 segments, we also have TP as 10 nanoseconds. We can find out the speed up ratio for n equals 100. So we will do ntn upon k plus n minus 1 tp. So it will be 100 into 50. 100 are the tasks n into tn times 50 for non-pipeline upon k plus n minus 1 into 10 for the pipeline. We get 4.76 is the exact, and the maximum that we can get is when we have tn and tp as same, which will be 50 upon 10. That will be tn upon tp, which will give us the value of 5. This is the time for 100 tasks, and this will be the maximum time of speed up that we can get. Both the formulas were studied in module 5, and you can go have a look at them. Next question is, the pipeline takes the following propagation times: 40 seconds for the operands to be read from the memory of register R1 and R2, 45 for the signal to promote to the multiplier, and 5 seconds to transform R3 to R3, 15 seconds to add the two multipliers into R5. So this will be according to a diagram where they have a pipeline system, and these were the times for the different tasks. So our task is to calculate what is the minimum clock cycle time that can be used in part A. So minimum clock cycle time will be the pipeline time, hence the pipeline time will be calculated by taking 45 plus 5, which we have from the following: 45 nanoseconds for the signal to propagate to the multiplier, and 5 to transfer from 3. Okay, so that is the minimum clock cycle where we are getting rid of the extra registers where we are storing. And B is, a non-pipeline system can perform the same operation by removing R3 and R4. How long will it take to multiply and add the operands without using the pipeline? So we are going to take the times 40, 45 and 15 seconds. 40 seconds for the operands to be read from memory, R1 and R2. 45 seconds for them to go to the multiplier, and since it was the R3 and R4 removed, okay, we have 15 seconds to add the two numbers. 15 nanoseconds, we add this time and we get the propagation time for non-pipeline system. Part C says calculate the speed up of the pipeline for 10 tasks and again for 100 tasks. So the speed up is calculated by S equals to NTN upon K plus N minus 1 TP. We have N given as 10 into 100, which is the time taken for the non-pipeline system, upon K plus N minus 1 and then 50. We have K as 3 segments over here, so 50 is K is 3 plus N minus 1, tasks 10 here. So basic calculation maths, you can find it out, 10 kile, and then you just put 100 instead of N and you can find it for 100. In D part you need the maximum speed up, so it is Tn upon Tp. You can find it, the maximum speed up is 2. When we have questions related to RAMs, we have how many 128 into 8 RAM chips are needed to provide the memory capacity of 2048 bytes. So this is a basic ratio question. We need 2048 bytes and the RAM has the maximum of 128 bytes. So 2048 upon 128 will give us the number of RAMs we need, which is 16. Part B says how many lines of the address must be used to access 2048 bytes of memory, and how many of these will be common to all chips. So 2048 can be simplified with the expression of 2 power 11, hence we get 11 address lines for 2048 bytes. And from 128, which is the RAM chip, we can simplify 128 into 2 to the power 7. Thus we have 7 lines to address each separate chip, which leaves us with the difference being 4 lines are to the decoder for selecting one of the 16 RAM chips. Part C is about how many lines must be decoded for chip select and select the size of the decoders. So we found out the how many lines for the chip select. We'll subtract the 2 lines that we found for the RAM and the memory, and then the difference is for the decoder. And since we have 4 lines to the decoder, so for 16 chips it is a 4:16 decoder. Similarly, in the next question we are given with a RAM of 256 into 8 and 1024 into 8 ROM chips, okay, and the computer system needs 2k bytes of RAM and 4k bytes of ROM. That means 2048 bytes of RAM and 4096 bytes of ROM. In order to calculate the values, we will perform the same way as previously. The RAM will be memory required upon the RAM memory. We'll get the number of chips, and ROM will be again the memory required upon the ROM size. We'll get the chips for ROM as well, and then we can calculate the address lines for the memories, which will be 2 power 11 and 2 power 12. Hence we have 11 for the memory in RAM and 12 for the memory in ROM. While taking the size of the RAM and ROM, we can find 2 power 8 and 2 power 10. Hence we have 8 address lines to the each chip in RAM and 10 to each chip in ROM. Using these values, we are now going to find out the mapping. It is important to learn how to draw the map for the RAM and ROM. So the first column talks about the component, which is the RAM and the ROM, and the address is given for the RAM and the ROM. We have the address ranging from 1 to 16 bits. So for the computer system, the RAM has only 8 bits in the input always, so we take from 1 all the way to the 8th bit as the address for the RAM, and it is denoted by X, as it could be anything from the minimum to the maximum. Same way for the ROM, it is from 1 till 9. ROM is represented to 9. We need 9 bits for the ROM. Sorry, in this case we have 10, so 10 bits for the ROM, hence 10 bits are denoted by X for ROM. That will be used for setting the ROM. Then the bits from 13 to 16 are always 0, or we can use the bits from 14 to 11. Any 4 bits are selected as always 0, and we are using the bits over here for the decoder. 2 columns will be chosen to select between the different components. So 00 means RAM, 01 means ROM, and 10 means the interface. For the address, we are supposed to take the minimum address all the way to the maximum address. We are going to take the minimum hexadecimal number over here, and then for 8 of the digits, we are going to, for all of these 16 bits, that will give us 4 different hexadecimal digits, we can take the maximum value. Since we will have 13 to 16 as 0 for the RAM, it will be 0, and then both of these can be maximum, so they'll give FF, and we have 9 to 12 as 7. Since we have 8 chips in the RAM, we have a decoder of these to it to choose one of the RAMs. So 7 will be giving us the range for the selection of the RAM. And in ROM, since we have 4 different chips in ROM, so we'll have a 2:4 decoder to select the ROM chips, and our addresses can be selected accordingly. We can find out the value of the last 4 bits as 4, rest all of them will be 0 for the minimum value, and the range of maximum will be 4FFF. That is how we can make the map for the RAM and ROM. Now in this instruction pipeline we have the RISC processor that has the following stages: the IF stage, ID, OF stage, PO stage, WB stage, and all these stages take 1 clock cycle for each instruction. Now we consider a sequence of 100 instructions. In the PO stage, 40 instructions take 3 clock cycles, 35 take 2 clock cycles, and the remaining 25 instructions take 1 clock cycle each. Assume that there are no data hazards and no control hazards. You have to find the clock cycles required for the completion of execution of the sequence of instructions. So since we have total 100 instructions and all of these instructions that were mentioned in the beginning are performed in 1 clock cycle each, so in the PO stage we have the following given, that 40 is instructions in 3 cycles, 35 in 2, and 25 in 1. So the average cycle that we have overall is 40 times 3 plus 35 times 2 plus 25 times 1, and then find the average for the instructions by dividing by 100. Hence we get 2.15 cycles as the average in the PO stage. Then on average the first instruction is completed in 1 plus 1 plus 1 plus 1 plus 2.5 cycles. This is because we have 1 cycle for each of these operations, which are 4 of them. So 4 plus 2.15 for the average PO stage gives us the average time for the first instruction to be completed. For the rest of the 99 instructions, we multiply them by 2.15 from the previous answer, 1992.55, which gives us the cycles for the remaining instructions. Finally, the total number of cycles can be the sum of our first instruction plus the remaining instruction cycles, which gives us 219.